Okay, yeah, so as I was saying, I'll try to finish the material um for the exam that we have on Monday day. So um let me see if we can do that. Or and if I don't finish on the material today, definitely like within the first few minutes um of class. Tomorrow we should be done. Okay. So what we were talking about last time was about this vector space stuff. So again, remember that for vector spaces, the idea is that you like there are two properties to check on a vector space. The first one is that if you have two elements in a vector space and you add them together, you get a new element of the vector space. In terms of equations, because usually the vector spaces that we work with are defined by some equation, what that means is that if you take two vectors that satisfy the equation, then the sum satisfies the equation again. It's just that you have to be a little bit careful there because, again, this concept of vector spaces can also be applied to matrices and things like that. So when I say vector here, I just mean something that is like a vector in the literal sense of the word, but it could also be like like a matrix or even a function, so though that's a little bit more tricky. So the sum of two elements belongs to satisfies the conditions again or the equations, and then the other property is like this rescaling property that if you have an element that satisfies the equation and you rescale it or multiply it by a number, then that element satisfies the equation again. Okay, so those are the two main properties. Today, what I'll tell you about is what's called the basis of a vector space, and that's kind of like the most important concept about vector spaces. So let's talk about that. So what's the idea of a basis? Uh, so the idea is that you're kind of so the goal is that you're going to have a vector space. So this is going to be a vector space. Okay, and a basis for this vector space um, will consist So the basis is made up by a couple by some vectors of the vector space, so such that each vi is an element of V, and then each V inside of V in V is a linear combination of the vi, and the last property is that the VIs are linearly independent. So the VIs are linearly independent. Okay, so you can think, you'll see in a moment, it's useful to think of a basis somehow as like the minimum amount of information needed to describe each vector of the vector space. So a basis is kind of like the minimum amount of information or vectors to describe every other vector. Oops. So let me give you some examples just to make it more clear to digest. So here's an example. I don't know if you remember, we had, well, let's start with something very even easier. Let's start with the vector space, which is R2. What is R2? R2 is just the name for the XY plane. So it's just the XY plane. So a vector, an element of R2 or an element of V is simply a vector on the XY plane. So an element of R2 is simply a vector on the XY plane. Okay, and so the idea is that every vector in R2 can be described in terms of two vectors. So these two vectors will be called a basis for R2. So the most basic basis of R2 is the following. It's called the standard basis. So if you remember, I may have mentioned these vectors E1 and E2 some time ago when we were talking about the inverse of a matrix. But you have here the vector E1, which is parallel to the x-axis, and you have here the vector E2, which is parallel to the y-axis, right? And what I'm saying is that any vector, any vector here, any green vector here, can be broken as a decomposition of E1 and E2, okay? So how can you do that? Well, V is x comma y, right? But what is x? Well, you can, it is convenient to write x as xy as x0 plus y0 plus 0y. And if you notice, like that gives you x times 1, 0 plus y times 0, 1. So what that is saying is that the vector v is x times the vector e1 plus y times the vector e2. Okay, so in other words, the vector V is a rescaled sum of E1 and E2. Is that making sense? So V is a sum, and it's not quite a sum in the sense like the coefficients are one, but it is a sum in the sense that if you allow the vectors to be rescaled first, then their sum to produce the vector V. So V is a rescaled sum of E1 and E2. Is that making sense? So in that sense, the is that we say that E1 and E2 form a basis for the plane, because every vector on the plane can be decomposed in terms of like of these basic vectors. So you can think, if you want to think of an analogy, in the periodic table, like the basis is kind of like the basic elements, and then like the vectors are kind of like more complicated molecules that you build out of the elements. So like the vector is kind of like water, so it's H2O. So like the basis is kind of like hydrogen and oxygen. So once you have here's like the analogy, right? You have something like water, which is H2O, right? So here, like the basis would be hydrogen and oxygen. So you're saying like kind of the water is 2 times hydrogen, right? Plus 1 times oxygen. So that is that's kind of giving water as a combination of hydrogen and oxygen. Is that making sense? So it's one way to think about it. Like, so it's breaking down the the a complicated molecule in things in terms of like more like elementary atoms. So that's one way to think about it. So a basis is kind of it's basically the idea is to have to be able to describe any vector in terms of two elementary vectors. Okay. Is that making sense? So that's one case. That's the most basic case. Here's another example. I don't know if you remember that we had discussed this vector space a long time ago. It consisted of the vectors x, y, z, where x plus y plus z equals 0. Not sure if anyone remembers what this looks like, but this was like a plane in 3 dimensions. So here you had x, y, z. And again, like here, you're not looking at all vectors with 3 entries. You're just looking at those vectors with 3 entries where, where the sum of each of its individual components adds up to 0. Okay. So there is a sense. So the idea is that there is a sense in which any vector that belongs here, you only need 2 numbers to describe it. The reason for that is because there's an equation that relates the 3 entries, right? So given that there's like an equation, in a sense, you can solve for one of the variables. So here's like a thing we could do. We could start, we could take the equation of the plane, or take the equation defining V, which is x plus y plus z equals 0. And you can solve it for z. So you can say that z equals minus x minus y. Okay? So any vector inside of V, right, can be written as x, y minus x minus y. Is that making sense? Is that okay so far, so good? All right, I'm just using the equation. I'm just using the equation of the plane to solve for the variable. And so then what we can do, once you have the vector written in this way, you can break the vector into two pieces, the piece that has x and the piece that has y. So let's just call this x0 minus x plus 0y minus y. And why do I do it that way? Because if I do it this way, then I can factor out the variable. So you can say that this is x like 1, 0 minus 1 plus y 0, 1 minus 1. Okay, but so that said, if you call this v1 and v2, this is precisely x times v1 plus y times v2. So it is a linear combination. So what this is saying is that any vector in the plane is a sum of the vectors v1 and v2. So any vector. So in the not in the xy plane, but in V, let me just say any vector in V. In the plane V is then a sum, is then a linear combination. And so they form a basis. Is that making sense? Let me see if I can show you this. Yeah, let me see if I can do this like here in GeoGebra just to make it more easy to see. So let me share the screen with you. So what I'm saying is that, for example, you can take the equation of the plane, like x plus y plus c equals 0, right? This is that plane that we have been talking about. So let me just change the colors so that it's like the same color that we had on the tablet. Okay, and then what I'm saying is that if you take, you can take two vectors. One vector would be 1, 0, -1. Okay, and the other vector would be 0, 1, -1. Right, so I'm plotting on GeoGebra the two vectors. In fact, it may be better to just see it. Okay, it is better maybe to just see it without the axis so that it's less confusing. So you see, I'm plotting these two vectors on GeoGebra. Okay, if you look at them, each of them is drawn on the plane, so each one belongs on the plane. And what I'm saying is that if you take a vector like which is a combination of these two. So let me use this with a different color so that it is clear that this refers to the one that's the linear combination. So if you take like a sum of these two, like you see, I'm just changing the names here to make it easier on GeoGebra. So use what I'm calling V1 on the tablet on the notes, and this is what I'm calling V2. But if you change, if you combine, if you're allowed to change the values for these coefficients in front of the vectors, so that's what I'm doing here. If you notice that I'm changing the value for A, I don't know if you can see it in the animation. And the same you can do that for V. Then what you end up doing is kind of like you begin describing every single vector on the plane in terms of these combinations of these two individual vectors. So you see every vector on the plane is a sum of these initial two vectors if you understand by sum like rescaled sum. Is that making sense? Uh, So that's like the point of a linear, that's the point of a basis, that once you have the basis, you can kind of find any other vector in the vector space because any other vector will be like a combination of these two. So let me stop here to go back to the tablet. Now, what's interesting is that any vector, like a vector space, can have more than one basis. So in fact, it will have infinitely many different bases. But so here's something important. The basis is not unique. So here's like something that's important. A vector space will admit several different bases. So let's just find another basis, for example, with the plane we were working with. So, let's go back to our word plane example. So back to the plane. So if you notice, what I did to find a basis for this plane was to use the equation to solve for z. But I mean, already here it's kind of clear that you didn't have to necessarily solve for z, right? You could have solved for one of the other two variables. That's like the easiest thing you could have done. So for example, we can solve here for x. And so now x is minus y minus z, right? So now if you have a vector in the basis, sorry, now if you have a vector inside of V, now if you have a vector inside of V, instead of replacing Z, instead of replacing C, you can replace X. Is that making sense? So now every vector in this plane is being described in terms of Y and Z. And then you can do the same as before. You can break it into the stuff with the Y variable plus the stuff with the C variable. Okay, and this is Y times minus 1, 1, 0 plus Z times minus 1, 0, 1. Okay, and well, I believe none of these two vectors are the same as the ones before, so let's call them u1 and u2, for example. So if you call this u1 and this one u2, this is saying that any vector v is a sum of y times u1 plus z times u2. So again, these two vectors u1 and u2 would form a basis for v. Is that okay? Are there any questions up to this point? In practice, that's correct. In practice, what you end up doing, I wouldn't use a well, let's call it vector, but instead of matrix, although it's true, like a vector is like a matrix, in fact. So yes, the idea is kind of like you use the equations that define the vector space to kind of try to solve for the variables, right? So that you kind of keep the minimum amount of variables needed. The thing that was happening in this problem, right, is that like here like the vector seems to be written in terms of three variables x, y, and z, but that's kind of an illusion because there is an equation relating the three variables. So really like what that means is that kind of like some of the variables are determined by the others. Which one determines the others is kind of up to you, so that's where there's freedom in choosing the basis. But the point of the basis is that you know you kind of want to rewrite the vectors in a way that just shows the minimum amount of information needed to describe them, right? So if you just write this as x, y, z, you're kind of like misleading people because it looks like it depends on three things, when in fact it only depends on two because like the equation relates the three variables. Is that making sense? But yeah, so in practice, you just do the splitting. Of course, what will happen in a couple of minutes is that there are cases where are a little bit more complicated, and that's where you have to kind of solve the system of linear equations to really figure out what's going on. But at least for the examples I'm starting with, the easiest, like you can do it like very concretely by just like replacing the variables. But yeah, like in a couple of minutes, once we do slightly more complicated cases, like what's easiest is just to like simplify the system of equations. How using the tools that we saw from the first midterm about reducing the matrix and things like reducing matrices and things like that. But yeah, for now it's just like a very simple splitting that takes place. Is that okay? So let's do another one. Well, you mean a problem like well, I'm still doing examples about this topic, or you meant like something different? Oh, so I see. So the thing is like okay, so you start with the equation of the, in this case you start with the equation that defines a vector space, right? Use it to solve for one of the variables. Like for example, I'm solving here for x, right? So that is what I'm plugging into here. So far so good. Once you get to this stage, you see there's stuff that there's stuff that depends on y and there's stuff that depends on z. So I just split it according to the variable they depend on. Is that making sense? Um, after, and then how am I getting these entry values? I mean, you can like it's kind of like how I mean, how do I know to put like a zero here if that's what you were asking? It's because this is kind of like zero y, right? And why do I put like sorry, this is kind of like zero z. Let me write it. I think I know what you mean. So I'll put it like -1y minus 1z, 1y plus 0z, and then 0y plus 1z. I don't know if that makes it more clear why I'm getting these numbers, because it is -1, 1, 0, -1, 1, 0, and then -1, 0, 1. So it's not that different from how we were, figuring out. It's similar to how we figure out like the matrix. Like this problem is about the find the matrix that turns this vector into this other vector type thing. It's just like, but it's literally the coefficients that multiply the variables, right? Like what these vectors end up being. Is that making sense? So like y is multiplied by -1, 1, 0, because there's no y here, and z is multiplied by -1, 0, 1. Does that? I'm not sure. Does that answer your question or? Uh, okay, let's do another one. Which is a little bit of an overkill, but just to show you how you could do this, like, and because that's kind of how we're going to do it in a couple more precise in a couple minutes. So here's another example. I believe I had given you this. Sorry, just to find it, show you that we had discussed this one before. I think we did this one yesterday at some point. Oh, here it is. So this is an example we discussed yesterday. So we talked about this one last time. So this one we talked about it last time. Okay. So now let's say you wanted to find a basis for this vector space. Okay, so now you want to find a basis for V. I mean, one thing you could do is to, again, do something similar to what I did before, like kind of start trying to solve for one of the variables. And that is very easy, like when there's only one equation. This case is a little bit more tricky. Still, the equations are simple enough that you could do that by hand. But I mean, that's the whole point of why we did the stuff that we did earlier in linear algebra, right? Where we were actually solving homogeneous systems or solving more generally systems of equations. So actually, you should think of these equations, right? These two equations define a homogeneous system, right? So notice that the equations of V. Uh, it's just that I have to show it more as a homogeneous system. I kind of have to move all the variables to one side because recall that that's like the standard convention for writing the systems of equations in this class. Like kind of like all the variables appear on the left side of the equation. Is that making sense? So these two equations are the same as these two, right? But how did we solve those systems of equations? What we would do is like, set up the matrix, right? So if you set up the matrix, I'll just, I'll put everything like, it's a easy system to solve. I'll like explicitly put the 0, 0 here just to make everything more convenient. Okay, and there's almost nothing to do to this matrix. But so how do you? But it's now conceptually we're thinking about it slightly different. Now we're not just trying to solve this system random, because it's a system of a homogeneous system. We're trying to solve it because you'll see it will give us like a basis in a second. So you can do -2 row 1 plus row 2 into what? Into row 2, and okay. And this is why I was saying that like solving reducing matrices is essentially kind of like the only thing we do in this class. So like once again, we're reducing matrices. So you get 0, 0 here. So when you do that, you put 0 here, and then this one becomes 2 with 1. Okay. If I'm making a mistake, just please let me know. So you get that, and then just to again make it super clear, I'll put a 0. To keep reducing this matrix, I'll put a 0 here. So how do I put a 0 here? I can do row 2 plus row 1 into row 1. Is that making sense? Is it clear that that's I mean, hopefully again, I hope I didn't make any mistakes. But that's one way to reduce a matrix, right? And so the point of reducing matrices is that you can, I mean, once you reduce the matrix, you can return back to the system of equations, right? So it gives you x minus z equals 0 and y minus 2z equals 0. Okay, but this is super easy because now this one gives you x and y in terms of z, right? So this one says that x is, let me use a different color. This one is saying that oops, this one is saying that x is z, right? And this one is saying that y is 2z. Is that okay? And so a vector, right? Like if you start with a vector inside of V, so a vector inside of V, well, it can be simplified because it was x, y, z, but I just showed you that x is really z and y is 2z, and z is just z, right? There's nothing that we did to it, this one. But so what that is saying, like, it's important to think about what this is saying. Is that saying that if you have a vector that satisfies these two original equations, right, is secretly a multiple. It is secretly a multiple of the following vector. You can pull out the C. Right. So what this is saying is that any vector is really a multiple of the vector 1, 2, 1. Okay. So in other words, the basis for this vector space is just really that vector, which we can call v1. Okay. Is that making sense? So far, so good. So this is actually, in a sense, the most almost like the most important type of, yeah, like of the all the vector spaces, like it is kind of covers a lot of those situations. So there are many situations where the vector space is just defined by equations set equal to 0. Okay, and so we need a name for that, and that's called the null space. So let me tell you about that. Just to give you a couple of useful formulas. So now we're going to talk about a very important type of vector space. Uh, and this is usually called null of A. So these consist, so the idea is like here, if you have a matrix, here you have a matrix. And the null space just consists of all the solutions to the homogeneous system of equations Ax equals 0. So the null space consists of all the vectors V Okay. So let me, so it's just like, you just look at all the solutions to the homogeneous system. So for example, here are some examples. So, you know, if the matrix had been like, let's do like a 3x3 matrix, which we'll discuss in a bit. Let's say I had given you 1, 0, 1, 1, 1, 2, 2, 1, 3. If I give you this matrix, then the null space of A would be the solutions to the homogeneous system. So it's the solutions to Ax equals 0, or yeah. So it is the vectors. What is the homogeneous system in this case? So it would be x plus z equals 0, x plus y plus 2z equals 0, 2x plus y plus 3z equals 0. Okay, so again, remember, like you could always go back and forth between the matrix and the system of and the coefficients that appear in the system of equations. So in this case, the system of equations is just this one. And likewise, like, you know, similarly, here's another example. Imagine I had defined like a vector, like vector space like X, the vectors which are X, Y, Z, W, where like, I don't know, what do we want? We want like X plus Y minus W equals 0. X plus 2Y plus Z equals 0. And then X plus Y plus C plus W equals 0. Imagine I had defined something like that. Then what is a matrix? Secretly, there's a matrix here, right? Because this is a homogeneous system in the sense that every vector is being set equal to 0. So B is actually the null space of a matrix, where A in this case is what? A is 1, 1, 0, -1, 1, 2, 1, 0, and 1, 1, 1, 1. Is that making sense? So I'm saying that there are many situations if the vector space is just defined using a system of equations where like a system of homogeneous equations where like it is that this serves its own name because it's just like a very common situation. So that's when that happens, you just refer to that as the null space. Okay. Is that making sense so far so good with this definition? So what happens in general, okay, so if I ask you to find a basis for this vector space, literally what that means, or for the previous one, what that means is to reduce the matrices, right? So that you can solve for the variables in the most efficient way. So what's nice is that there's like a theorem called the rank nullity theorem that tells you how many vectors you will always find in these bases. So that's that's one of the most important theorems in all of linear algebra. So let me write that down well precisely so that because it's kind of like a useful piece of data, and then we can see how it looks like in our particular case. Okay. So I'll show you how that looks like again in these two cases. So this is called the rank nullity theorem. Again, this is like one of the most important results of all of linear algebra. So this is really important. I mean, we won't prove it, but the book may discuss a proof. I'm not 100%. I don't recall at this moment. But what it says is that if you have a matrix, if you have an n by n matrix, then the null space, right? Then the null space so again, this just means that solutions to AX equals 0 forms a vector space. Okay, that's fine. But like the most important, like that's okay, that's good to know. That's actually not difficult to check. Because if you have two solutions here, since this is being equal to 0, the sum will continue to equal 0 here. And if you rescale it by a vector by a number, since this is being set equal to 0, like the rescaling doesn't matter. So checking that that's a vector space is not the big thing. The more important thing is how do you find a basis? To find a basis, let's see. So to find a basis, for the null space, you just reduce the homogeneous system. Okay, you reduce the homogeneous system, the matrix A, to its row echelon form, or the homogeneous system. Let's put it like this. Until reaching the row echelon form of A. And the number of vectors that will appear in the basis. So what that's actually called a dimension. So let me write it down because it's an important idea. So the dimension of the null space. So this means like when I write here dim, that just means the dimension. And that's just like the number of vectors in the basis. Okay. So this is the number of vectors in the basis, in your basis. I'm about to show you with these two examples so that you see how this looks like. So the null space, which is the dimension of the null space, like how many vectors you will end up occupying in that basis, that's actually the number of columns of A minus the rank of A. And this is called this is what sometimes is called or usually it's called the nullity of A. But it's better just to write it as number of columns minus rank. This is called of A. Okay. So the cool thing about this result is that it gives you like a precise number for how many vectors you should expect to see in your basis. So that kind of like is like a reassurance. I mean, of course, like you would always find the correct answer if you reduce a matrix correctly. But if you make mistakes, it's kind of like good to have like a separate way to verify how many vectors you would expect. Okay. So again, I'm about to give you some examples for that, but it's literally doing the same thing that we were doing before, which is reducing a matrix. Is that now we're giving it like a slightly different interpretation because that's giving you like that's helping you kind of find the basis for the vector spaces. So that's like one of the important ideas of like reducing a matrix to find basis for vector space. Is that making sense? So just give me a second. So okay, let's do this in two examples so that you see how this looks. So I had given, let's say I give you D, which is a vectors that solve X, Y, Z, which solve again this which solve X plus Z equals 0, X plus Y plus 2Z equals 0, and 2X plus Y plus 3z equals 0. Okay, and so I want a basis for this. So the problem would be to find a basis for b. So again, because it's a homogeneous system, right? So B is defined using a homogeneous system. Right, what's the homogeneous system? Ax equals 0, where A is the matrix what? A is the matrix that I wrote earlier. A is this matrix, right? What I'm going to do is to just reduce the homogeneous system. So let's reduce A. So to reduce A, how do we reduce? I mean, reduce a homogeneous system. So just to emphasize that, of course, like reducing the homogeneous system is not too bad because like there's a bunch of zeros on the left column. So like you don't really need to keep track of those, but it's more convenient at this point to do that. So to reduce A, like you do the row operations. So let's do minus row 1 plus row 2 into row 2, and I'll do minus 2 row 1 plus row 3 into row 3. Is that making sense? And then usually these problems, like the matrices, are easy to reduce because the most important thing is like the theory behind it of finding the basis. So now you have to, it's kind of clear that the second and third rows are the same. So you can do minus row 2 plus row 3 into row 3. And that will give you what? 1, 0, 1, 0, 0, 1, 1, 0, and then 0, 0, 0, 0. Okay. And then, well, that's more or less the best you can do, right? Because to put a 0 here, like it would necessarily undo the 0 that you have here. So this is the reduced form. So again, like what's the rank of the matrix? The rank is going to be 2. Is 2, right? There are 2 non-zero rows. And then what's the number of columns? The number of columns is 3. So what I wrote before, like the rank nullity theorem, what it says is that you should get 3 minus 2 vectors in the basis. So the dimension of the nullity is going to be number of columns minus rank. So it's going to be 3 minus 2. So it's going to be, so what that means is that we should expect one vector. The basis will consist of only one vector. Okay, and how can we find that vector? So again, it's not that you kind of need to check this step. I mean, you would still figure it out once you write everything out, but it's just kind of nice to know the answer ahead of time. So if you notice, like this system of equations is the same as x plus c equals 0 and y plus c equals 0. Okay. So again, everything ends up being in terms of y, and everything in terms of being in terms of c, and so the vector is just x, y, c. It was like now minus c z. So this is just c times -1, -1, 1. And so this is the basis. Hopefully it wasn't the same. Was this the same example as before? Well, in oh no, it's similar, but yeah, it's different group. Okay, so that's how you find the basis in this case. Well, you can ask me about that one in office hours if you want. I'll probably just do what we had done like one time some lessons ago, like just instead of having the quiz today, I'll just give you like an assignment to complete because I'd rather just finish the material for the exam today than having the quiz. So like yeah, what I'll do is just give you like 4 problems to complete by the end of the week or something like that instead of the quiz. Like an assignment, just to prioritize finishing everything today. No, I will just turn it into an assignment. Probably like most likely the one on Thursday as well. It's just I want to get some topics. The problem is that we don't have that many classes left, and I don't want to, cover like a lot of material the day before the final. That's kind of a bit mean. So I'm trying to, like, at least probably for this week, yeah, I'll just give you like a longer assignment instead of like the 2 quizzes. And then depending on how we're going with the topics, and yeah, probably we can return to more regular quizzes. Correct, yes. Most likely no quiz on Thursday. So either like I'll just give like an assignment that counts for both quizzes instead. Just to, get more material done this week. So no, it would be due Saturday or something like that. Yeah, well, Saturday or Sunday. I mean, by the end of the week, usually before the exam, because it would be on topics about the exam. So, yeah, I think Saturday should be enough time. I mean, today I'll try to finish the material for the exam. Yeah, it's like a combined assignment basically, but it won't be that long. It would be like 4 or 5 problems. I think we had done that before, like for the first midterm, if I'm not mistaken. So, correct. Yeah, it's just like I add up the quiz 2 quiz points, and that's like what the assignment would be worth. Yes. So it would be like 36 points, I think, because usually the quizzes I have been making them 18 points, if I'm not mistaken. It will like it's determinants correct and hopefully up to today. But I'll give you like a study guide. If I don't finish everything today, like say like the first 30 minutes of tomorrow, there are not that many things left. But yeah, it's basically determinants and vector spaces. Yeah. Let me give you another example that sounds good. So let's do this one. Yeah, so we're almost done with the material for the exam. Like, yeah, that's what. Oh, sorry, I forgot about that. I will give you once. Like, I'll give you. Yeah, that's how you should compute your grade on the exam. Just add up both parts. I'll send you like an announcement. Once I post like the study guide, I'll also let you know like kind of like your letter grade for the exam. I just forgot about that. The exam scores were pretty good. I think the average, like in the first part was like an 80. I think the average between the two exams like was 78 or something like that. So it was overall, I think you did pretty well. But yeah, I'll send you like an announcement like saying, well, if you got this, that's kind of like an A, or if you got this is like a B. I just like I totally forgot to do that. I'll do it once I send you the information for the second midterm. I'll put that as well on the announcement. But yeah, I think you did pretty well. So, well, it is. It's kind of both at the same time. Like if if the scores are going well, then yes, it's based on 500. But if the scores don't go that well, then like do some help and curve the grades a little bit. So it's kind of like it can be curved if it's necessary just to help with the overall performance. So in the sense like you kind of just have more generous margins for where an A or B or C starts. Well, my rule of thumb is that anyone who gets more than like 90% of the course like should get an A. But like again, like sometimes like an A can start below that, like but yeah, anyone who gets like a 90% would get like an A for sure. So, which is like 450 points. So, but then again, it could be lower than that, but depending on how people are doing. So it's not setting. So well, you just look at like the overall performance, like so.
Professor, we don't have a quiz today, right?
Correct.
Okay. By the way, could you like end off the class to explain a little bit question 57, if you can?
Well, we can go over during office hours if you want, if you can stay over the class.
Okay.
I mean, it's just kind of like how all the courses, I think, in the math courses are done, like in terms of the letter grades. Like if you got like a certain minimum number of points, then you would get like a letter grade. But sometimes, like there's not like people don't do as well, so you just like increase the threshold for like getting that letter grade. Well, that's on the syllabus, right? It's like 150 points, I think. I believe so. Oh, well, maybe like, I'm not sure, like 10. It's 3 hours long, but well, I just said like probably 10, but if you want, you can ask me during office hours. I'm kind of not too sure. But yeah, not 20 questions. Right, as I was saying, for the null space, you have to solve the homogeneous system. And then let's just solve it here. No, I think for the reviews, I would just send you to the reviews I did on the spring semester. Like I'm kind of breaking the midterms in the summer so that they match with the same topics as in the spring, so that you can just watch those review videos if you like. So that's why I'm breaking in the topics that way. So yeah, they're like, I have recorded 2 review sessions like in the spring, and so if you want to watch those, you can. But it's essentially the same problems. So somehow like you have more just simply more classes on the spring because this is a 6 weeks class. So in fact, like if you count the number of lectures, it does you end up having a little bit less lectures here than than in the spring semester. So yeah, it's just like on the Zoom chat, the same Zoom chat, correct. So yeah, so here you have to reduce this to you can do this, and then you can also do you can do this, so you get 0, 1, 1 minus 1, 0, right? And then here you get 0, 0, 1, 2, 0. And then is that okay, right? Yeah, I think that looks good. And then you can put like a 0 in here. Let's put a 0 in here. So let's do minus row 2 plus row 1 into row 1. And then we'll we're almost done, right? I just need to put some zeros in here. Oh, let's see. Oh, this one, you're right. You mean okay, thanks. So I'm doing minus row 2 plus row 1. So this is why I think I got a -1 here, but this becomes a 1, so it becomes 0, right? Is that what you meant? Or I just wanted a 0 in here, right? So I had to do minus row 2. Is that making sense? Oh, okay. I see what happened. Let's see. Yeah, you're right. I see what you're saying. Like you're saying that here it should have been 1, right? Because, thanks. So, because if you do minus row 1 plus row 2, this becomes a 1, good. And then when you do minus row 2 plus row 1, yeah, this actually becomes what I had. Well, I don't know if that's what I had before, but yeah, thanks. I need to fix this a little bit. Is that better now? Let me check again just to make sure like I didn't do anything else. Let's see. Minus row 1. Yeah, that looks fine. And then this like, yeah, I think this is okay, right? And then minus row 2 plus row 1 gives you, yeah, is that okay? Is that making sense? Yeah, and then to get to finish reducing the method, you just put like two more zeros. So you could do minus. You could do row 3 plus row 1 into row 1, and then you could do minus row 3 plus row 2 into row 2. Okay, so you get what? 0, 0, 1, 2. Is that making sense? Is that okay? Just let me know if you find something else that looks like a mistake. So assuming this was correct, then the rank, I mean, that's definitely for sure going to happen. So the rank was 3. The number of columns is 4. So the dimension, which again just means how many vectors you will find in the basis, the dimension is just going to be in that for the case of a null space, it's always columns minus rows. Sorry, number of columns minus the rank. So it's just 4 minus 3. So that's just 1. So what that means is that we should expect to see like a single vector in the basis. How can you tell that? Well, you should write that back again as a system. So if you write this as a system, you get x equals 0, then y minus w equals 0, and z plus 2w equals 0. And so, I mean, again, this one is easy, just telling you what the value for x has to be. X always has to be 0. This one forces y to be w, and this forces z to be minus 2w. So you see everything is determined by w. So a vector x, y, z, w is just x is 0, y is w, z is minus 2w, and w equals w. Okay, so E is everything is a multiple of w. It's w times something. So everything is a multiple of this vector. So the basis is this vector v1. So this is the basic. Is that making sense? Yeah, that's actually what I was going to explain right now. That was the last topic for today, actually. It's very similar. I mean, you'll see, just still reduces the matrix, and then you're done. But yeah, that's what I was going to say next. But I think the null space is kind of like it's probably a little bit more important just because many things are secretly like the null space. Well, not necessarily in terms of a single variable. Sometimes it could be more than a single variable. In these cases, they do happen to be in terms of a single variable, but I think we did I believe one we had done before. Yeah, like for example, if you look at this original problem, actually everything ended up being in terms of two variables, right? So it's not that you always find like a single variable. You just find as many variables. I mean, the cool thing is like how many variables you end up finding is literally determined by the number of columns and the rank of the matrix. So it's just that in many cases it happens to be like one or two, but because we're working with matrices which are really small. But how many variables you end up with is determined by the rank and the number of columns. Is that making sense? So again, like in this example, if you write, it's just like it's kind of silly to write it as a matrix because the matrix literally just has one row. But that's we can actually write that down to go back to this plane. How does it look like from this perspective? Let me write it down because it's very quick. If you go, yeah, if you put it here, it's still a null space. It's just kind of like a very simple null space because the matrix A is just, A is just 1, 1, 1 in this case, right? So the rank is already 1, right? And the number of columns is still 3, right? So columns minus rank is 2, and that's why you end up with 2 variables. Is that making sense? And that's why the secretly was saying that you could write everything in terms, so everything could be written in terms of, so there were 2 basis vectors in this case. So 2 basis vectors. Which were the ones that we found before. Is that making sense? So it's not that you always end up just with one variable. That's what I'm trying to say. The number of variables you end up with ends up being, the determined by the number of columns and the rank. Is that okay? But yeah, just to kind of mention this up, there's like 2 more vector spaces that are important to keep around, which is called the row space and the column space that someone asked in the chat. So it's essentially will be kind of the same idea. So So these are called the row and column spaces of a matrix. So let me explain what the point is here. So you could have, like, let's start with a very you know, let's start with a very silly case, just to kind of show what's going on. So imagine that you have this matrix. Again, it's super simple. This is a 3x2 matrix, right? So if the thing is, like, you can think of a matrix in two different ways. You can think about it as a bunch of rows or as a bunch of columns, right? So in the row picture, right? So in the row picture, you think of a matrix as a row, a bunch of vectors formed by the rows. So in the row picture, you think of the matrix as a bunch of rows. As a bunch of row vectors. So in this case, like, what's the first row vector? Let's call it R1 for row. So 1, 1, and then the second row vector is 2, 2, right? And the third row vector is 3, 3. Okay. The thing is, like, these are vectors, right? It doesn't, like, something is a vector. It doesn't matter too much whether you decide to write it as a row or a column. It's just that it has been more convenient for us up to now to write them as column vectors. But I mean, if you write a vector as a row, it's also, like, not ambiguous what you mean. So the row space of a matrix is simply the vector space that consists of all the linear combinations of the row vectors. So there's this thing called the row space of a matrix. This is called the row space of a matrix. This is just a vector space consisting of all the vectors which are linear combinations of the rows of the matrix. So in this example, in our example for this matrix A, so for the matrix that I'm writing right now, it consists of all the vectors which can be written as because remember, like a linear combination is just means take the original vectors and add them together after maybe doing some rescaling. So it would be like C1, C2, C3, row 1, row 2, row 3. So right, again, this is kind of important to remember. A linear combination just means like you have some vectors which you're adding, but before adding them, you're just allowed to multiply them by numbers. Now, I chose like a very I'm starting with this very simple example because there's something that is maybe kind of obvious in this case. I don't know if anyone like for this particular case, right? I don't know if it's clear that there's like well, I don't know how obvious it is that there's like a relation between these different row vectors. What can you say about the row vectors here? So it would be like can anyone tell something that's happening here with the row vectors? How is the second one related to the first one, for example? They're just multiples, right? I chose it so that would happen. So because again, I'm trying to warm up with this example. So this is like 1, 1. But the second one is 2 times the first one, right? So you can write this as 2C2, 1, 1. And the last one is 3 times, like I can write this in also blue. And the last one is 3 times the first one, right? So you can write that as 3 C3, 1, 1. So why am I doing all of that? Just to emphasize that my point of doing that is that in fact, just because like what I'm trying to do here is like just to explain that just because a matrix happened to have 3 rows doesn't mean that you needed 3 rows to describe all the linear combinations, right? Because there were secretly some relation between the rows. So just because, so what's the point of this example? Just because just because A has 3 rows, that doesn't mean that you needed 3 different vectors to describe all the linear combinations. In fact, here, only 1 vector was enough because all the 2 remaining ones were multiples of this one. That doesn't mean that 3 vectors are needed to describe all the linear combinations. In fact, how many vectors? Because there are redundancies, right? Because sometimes there are redundancies among the vectors, because sometimes the rows are redundant. So in fact, how many rows do you think you actually would need in the end? There was a way that we had to, kill redundancies in a matrix, right? There was a way that's the whole point of the row operations. The idea of the row operations is to kind of eliminate redundancies in the rows of the matrix. So in fact, the nice thing is that the number of vectors that you need to describe the row space is literally the rank of the matrix. So let me write that down as a theorem. So the idea is like if you wanted to find a basis for the row space, you reduce the matrix. and the non-zero rows of that matrix are the bases. So to find a basis for row of A, reduce the matrix A, and the non-zero rows are the basis, and the non-zero rows form the basis for row of A. The non-zero rows of the row reduced echelon form make a basis for row of A. So again, you see, like the same that we were doing before, it's just about reducing a matrix. It's now the only difference is that now we're giving like a slightly different interpretation to this. So you can write that as saying that the dimension of the row space, again, which is like this is the number of vectors in the basis. In a basis of row of A. That's just the rank of the matrix. So that's another reason why the rank was actually important, which may not have been obvious at the beginning. The rank is also useful to specify the dimension of this vector space. So let me give you some examples. Well, let me give you a second to copy this, and I'll give you some examples. So yeah, so let's talk. Let's do like the one that we were just doing. So here's like an example with A equal to 1, 1, 2, 2, 3, 3, again, which is very silly. If you do minus 2 row 1 plus row 2 and minus 3 row 1 plus row 3, right? This gets you to 1, 1, 0, 0, 0, 0, right? So the rank is 1, right? So that means that the basis for the row space was just the non-zero row. So there's only one non-zero row. So the basis for row of A is the vector 1, 1. Okay. Well, let me give you a second to copy this. Here's another example that we had done earlier. So here's another example. I had given you, what was this matrix I gave you before? Sorry about that. So I gave you before this matrix, right? we had considered this matrix before, and we had reduced it, right? We reduced this one to what did we get when we reduced this matrix? Sorry, let me copy paste that again, just to show you that we had already done that. We got this matrix, right? So in this case, the rank was 3, right? The rank was 3. That's actually we had found before. So the dimension, what that means is it's actually 3 basis vectors were needed. So the basis consists of V1 being 1, 0, 0, 0, V2 being 0, 1, 0, -1, and V3 being 0, 0, 1, 2. Okay, so the basis of row of A, just to emphasize. Okay, so that's like what's okay. So that's the only thing that's a little bit tricky that can be easy to get confused by. So what's the difference between row of A and the null space? So maybe I'll end up with this here, and tomorrow I'll tell you about the column space because it's essentially the same idea. So here's like a remark. What is the difference? The difference between row of A and null of A. Well, in both you have to reduce the matrix A. So in both you'll do the same reduction. Both require reducing A. But for row of A, you just look at the non-zero rows of that matrix. For row of A, you look at the non-zero rows. And for null of A, you have to rewrite it as a homogeneous system to you know solve for the variables. So for null of A, you rewrite it as a homogeneous system to solve for the variables. So they can be they can look very similar, but the difference is that in the null space problem, it is always a homogeneous system. So you have to solve a system of equations at the end of the problem. So you can reduce the matrix. You can reduce the matrix in the same way in both, but in the null space, because it's a homogeneous system, you have to go back to writing everything in terms of the variables. Okay. That making sense? So that's like that's the difference. So the null space is always a system of equations. So you always need to do that. Okay, and that's more or less all of it. The only thing that I'll explain tomorrow quickly, because this is the same idea, is that how the column space is defined. So tomorrow what we will talk about is the column space. The column space, but that's just going to be the row space of A transpose. So it is not that different from what we have been doing so far. So this will be the column space. So I'll so it like it is still computing a row space. Yeah, I'll recommend the problems, some practice problems. What I'll try to send you today the study guide for the midterm. So if I get that done, I'll also recommend those as well. Okay, so but yeah, this is so I'll finish that tomorrow, as I was saying, but it is not that you have to I mean, the way we would do it, there is like a theorem in the book that would allow you to kind of it's better to transpose first. You could reduce first, and from there you can still extract the column space. But it is more confusing. So usually, like in practice, I won't ask you to compute both. If I give you a matrix, I will either ask for the row or the column space. So you have to reduce. It's not that you would reduce it twice. So it's better to transpose first. But yeah, there's like a way to do it without transposing first. But it just it's just more confusing. No, as I was saying, I'll put an assignment instead of the quiz. But yeah, like so the way I'll do it in the class is that you always transpose first. But yeah, if you read the book, there are other tricks to find these column spaces, which you're welcome to use. It's just I find that you have to explain why the trick works, and so that takes a little bit more time. So better just to look at it, I think, by transposing first. But yeah. Well, it depends on what you mean. Would it always be linearly dependent? What would be linearly dependent when you say that? What are you referring by always here? Oh, well, it's not. So, it can be like it depends. Okay. It can be the case that like it's kind of like a silly case, but it's not that interesting. But sometimes the null space could be zero because, like, if say for example, if you have like a matrix with a matrix which is invertible, right? If the matrix is invertible, then the homogeneous system always has a trivial solution, right? So all the variables kind of go away. So like x equals 0, y equals 0, z equals 0. It's just that is up, like in practice, like that can happen, but for like examples, like the examples that are interesting is where like there's some relation between the variables. You know what I mean? Because if the matrix is just invertible, then you have to do not too much. Is that making sense? But yeah, it is possible. Like like just to give you like a quick example, like you could have like and this is easy to solve, like without like matrices, but you could have something silly like this, right? Because the matrix is now 1 1 1 0 1, right? So if you look at the null space for this one, if you look at null space for this one, it's doing 1 1 0 1, right? But of course, like this is the same as like 1 0 0 1. So that just forces x equals 0 and y equals 0. So there's, I mean, that what happens here is like the rows and the column. I mean, both the rows and the columns of the matrix were linearly independent. So the null space, like the basis for the null space in this case is 0 0, right? So basis. Which can happen. I mean, it's just like that one is slightly less interesting. It's a vector because like it's kind of more entertaining to find null spaces which are non-trivial, which is like the word for it. Is that making sense? But it's a good question. Yeah, I should important to notice like the null space can be the zero vectors. Yeah. Is that okay? Correct. That can also, yes, that like for that you check at the rank, because like say for example, if you started with a matrix with 5 rows and the rank ends up being 3, that means that among the 5 rows there had to be some relations, right, to reduce the rank to 3. So that's very easy to tell from the rank that there were some there were some dependencies. Is that making sense? Because like if the rank ends up being less than the number of rows that you started with, that can only happen if there were some relations between the rows, for example. And for the column space, I'll talk about it tomorrow, but yeah, so I can go say that as well tomorrow. No, yeah, that's useful. Thanks for asking that. Okay, so if you want, just give me 2 minutes. I suppose like some of you are maybe staying for office hours, so give me 2 minutes and then I can answer your questions if you want. I mean, I can also record this, I suppose, as well. Nothing gets lost. So I'll just give me